In 1985, scientists discovered that chemicals called chlorofluorocarbons, or CFCs, were damaging the ozone layer, especially around Antarctica. Here, the ozone layer had become so thin that it was like a hole in Earth's shield of ozone, allowing dangerous radiation to reach the surface. The good news is that just 2 years later, more than 100 countries agreed to ban CFCs. Because of this international agreement, the ozone hole is now healing. I'm Science Mom.
I'm Math Dad.
Today we'll explore one of the most encouraging and terrifying stories of the century. Hello, and welcome to Mikal and Amir watching from Ottawa, to Charlie, Harold, and William.
Savannah. I love cats, meow. Jody Shoemaker. You guys have great names. I like this.
Elsa from South Carolina, Katie and Max from Ottawa. Good to see you guys here this morning. So we are going to be talking about ozone today, but before we can talk about ozone, we need to understand a couple things about light. So I have two different types of flashlights here. I have a UV flashlight and a regular flashlight.
Okay.
And we have a special type of paper, and we're going to see if these two lights make a difference.
Oh, so the different types of light are coming out of these two flashlights?
Yes. So I'm going to put these lights on a piece of paper, and I'm going to turn them on. You can see they're here. Go that other view. Yep. Get that other view. So these lights are really quite bright, and they're both on. I'll just lift them up a little bit so that you can see. This paper is special paper because it's reactive to light. So if I take this piece of paper and I dip it in water, it's going to wash away the blue dye and end up being white.
Wait, so is it reactive to light or to water?
Well, okay, so the dye is reactive to light, but the dye will wash off in water.
Okay.
Now, let's take our little experiment here where we had our lights on. I'm going to turn them both off.
Okay.
And take them off.
Ooh.
Look at this. We have circles here. And now when I dip this in the water,
okay,
I end up with a photograph, essentially, of these two light spots.
Well, that's really cool.
And it takes it just a minute to develop. These spots will look a little bit more blue as some time goes on. You can see that our UV light was really giving a lot of power to this paper. The visible light one, not quite as much.
So let's look at the face of that UV light. It's got all those diodes. That's what we're seeing there. Okay.
Now, if you want to try an experiment like this, you can do this with photo paper, and we got SunArt photo paper to do this, but you can also do the similar thing with just regular construction paper. And if you have ever put a piece of construction paper outside and then come back a day or two later and it's turned almost white, then you've seen this same reaction happening before. Dark blue construction paper will turn just about this light if it is left outside for a while because of the UV light.
So that's what we call bleaching?
Yes, bleaching or fading. Let's see if we can make a picture of this fidget spinner. You ready, Math Dad?
Yeah.
So what I'm going to do is just lightly shine this light, which is a UV light, over this paper. And while I'm doing that, Math Dad, let's play a quick little video about light.
All right.
Because light is very different. Nope, not that one.
Do you have it in here?
Yep, right there. Sorry, guys. There we go. We did it. Light is very different than paint when it comes to mixing colors. If you mix blue, green, or yellow and red, you're going to get brown. Those colors will mix together to make brown. But if you mix together different colors of light, you are actually going to get closer to white. So here we have three spotlights that were shining on the wall. A red one, a blue one, and a green one. I know it looks kind of yellow, but trust me, it's actually green. And if we overlap them, the red, the blue, and the green, in the center, we get white. And here with a blue and green, you can see anytime that we change the light, the shadows change. With just one light, we just get one shadow. But if we have two lights, we get two shadows, and their colors are different. And then if we add all three lights together, we're actually going to have three different shadows. And why do we see different shadows? It's because our lights are shining from different angles. But look at the way we get different colors. We're not shining any yellow light on there, but I'm getting a yellow shadow because of the way that the red and the green are overlapping.
Okay, that's really cool.
Isn't that cool?
Yeah.
So these are two different color systems. And if you've ever done any work designing or building graphics, you know that it really depends on if you're talking about a digital picture or not. Because if it's digital, you want RGB.
Oh, so at the very end where it showed the
RGB versus the CMYK.
yeah, like a printer. Yeah, yeah.
Now let's take a look at our little experiment here. I see a
Ooh.
shadow from our fidget spinner, and around the shadow, it's a little bit white. This means that our UV light has changed the paper. It has enough energy. It has changed how this paper works.
So there's some chemical reaction that took place there.
And if I dunk it underwater and rinse it real quick, and then set it down, we get a picture. Pretty cool, right?
I like that. Now, I'm noticing here the color is swapped. At first, where the flashlights were, that had been white.
Well, it takes it just a minute to develop. So you can see that where we shined the bright light, it turned really dark blue. And then here, where we were shining the light is blue, but where there was no light, it's white. And remember, this was the opposite, where we had the lights right on the surface.
So wait, is this one going to swap?
This one already swapped. All right.
Oh, the shadows are in the reverse spots.
Yeah.
Okay, that's exactly what you said. Sorry, I was just determined for that to change colors.
No worries, Dad. No worries. Okay, so light is energy. And if you have a wavelength of light that has a lot of energy, you can think of it as being a wave that's moving like this. So Math Dad, if coming this fast toward you was a wave, and one of the waves was like this, and the other wave was like this, which wave would you be afraid of?
Oh, someone's going to lose an eye with that second wave.
And that is how light is. Light always moves at the same speed, but if you have a high energy wave of light, that's like one that's going like this, up and down, super, super high energy. And it has power to actually cause molecules to break apart.
Oh, wow.
And
wait. We've seen that with blue skies, right? Blue skies are caused because the high energy blue light is actually colliding with particles and it's scattering.
Yes.
Right? Aha.
Now let's real quick look at our ozone layer and talk about what ozone is, because this is why we're talking about different colors of light. We want to understand what ozone is.
So just a second. So the blue light I was just talking about. So violet light is even more.
Violet light is even more energy.
Energy rich. And then ultraviolet is even further along the spectrum, more energy still. Is that correct?
Yes. Ultraviolet light has even more energy than blue light. So if you're looking at colors of light, red light is kind of like this. It's our friendly light. Blue light has more energy. Ultraviolet light is the dangerous, super energetic wave of light.
Gotcha.
Now, ozone is a molecule that is super interesting, and it's made of oxygen. If you have one single oxygen atom, this is actually pretty reactive. Oxygen likes to be paired. It likes to be paired with two of them together, O2. But if we add a third oxygen molecule, now we have O3. This is what ozone is. And ozone is reactive. If it bumps into a water molecule, boom, you're going to have a chemical reaction. If it bumps into another oxygen molecule, boom, chemical reaction.
Wait. How can we breathe it?
No.
But doesn't our body just take the oxygen away?
So if you breathe in ozone, this is considered to be very bad, because when you breathe in the ozone, it's not going to stay ozone inside your lungs. It's going to react, and there'll be oxygen. Oxygen in your lungs is fine. But this little guy, a free oxygen atom that's going to bang into things and cause all sorts of reactions, damage your DNA, this is not fine.
Oh.
So if you breathe in too much ozone, you can actually feel a burning sensation in your lungs. And if you have asthma, it will cause you to have a really bad asthma attack. Ozone down at ground level is considered a pollutant. We do not want ozone in the troposphere.
Ooh.
But ozone in the stratosphere is kind of amazing.
Wait, so it's bad for us near us, but it's good for us when it's far away?
Yes.
Okay.
It all depends on elevation. Ozone down in the troposphere is definitely bad. It harms both animals and plants. If there's too much ozone, you're going to have damage to cells. DNA is going to be breaking apart. Cell membranes are going to be breaking apart, and that is not good. But ozone up in the stratosphere is like a shield over our planet, protecting it. And here is how it works. This is pretty amazing. Let's go back to our other view, and I'm just going to show you with these little atoms. So when you have oxygen in the atmosphere, in the upper atmosphere, you have high energy radiation from the sun that is hitting the gas. And when high energy UV light hits this gas, it breaks apart into 2 single atoms. And then when one of those single atoms of oxygen bumps into another oxygen, it makes ozone. And this is how the ozone cycle works. And it is a cycle because the ozone molecule later on is going to bump into, it's going to split apart, absorb some light, and then reform. And this is happening over and over again.
Wait. So why is it breaking apart?
It's breaking apart because there is a constant amount of light coming from the sun. And when high energy light hits ozone, it absorbs that light and it breaks apart. And then this molecule collides with another oxygen.
So that atom
yes.
collides with the oxygen molecule to make an ozone molecule.
Makes it again. And the whole entire time this is happening, it is absorbing dangerous UV light. Absorbing it. And that's why the stratosphere is warmer. The ozone is heating up the stratosphere by absorbing all that radiation.
Oh, warmer than the air below. Ozone layer had a hole. Airplane contrails white like snow in the stratosphere.
Exactly right. And the types of radiation that ozone absorbs are super dangerous. Let's go to the notes real quick. We're going to be on page 42 and look at a little graph.
Okay.
The sun produces so many different types of radiation. Some of those waves of radiation have lower energy, like the light that we see. And the light that we can see makes it all the way through the atmosphere. And this is good for us because we like to be able to see, and that light is used by plants for photosynthesis. But higher energy light, the UV light, that is absorbed by the ozone layer.
Okay, so what I'm seeing here, if I draw this out, here's the ozone layer, and visible light goes straight through
all the way through.
The UVA light goes...
Most of it goes through.
Okay. UVB light, though...
Almost all of it gets absorbed. Only about 5% makes it through. And then UVC light, all of it is absorbed by the ozone layer. When you buy sunblock, if you buy sunblock at the store, you'll see that it will say blocks both UVA and UVB. We care about both of these types of UV radiation. The UVB is not very common, but it's more powerful.
So this is what would give us sunburns.
Yes, both of these types of radiation will give you a bad sunburn. And this is why my UV flashlight has a warning label on it and says, don't shine it in your eyes, keep it away from children, because UV light can be damaging to us.
But UVC wouldn't give us a sunburn, right?
UVC would give us an even worse sunburn. This type of UV light is even more powerful. It has a higher wavelength than the other 2 types of light. And we are so fortunate that the ozone layer blocks most of these 2 types of UV light.
So that, ozone is bad to have with us, breathing it in, but it's awesome to have up in the air, protecting us.
It really does act like a shield. Now, to understand why we've had a problem with ozone and why we talk about the ozone hole, we need to cover 2 more things really fast. First, I just want to point out, if we can go to this view again, ozone is formed naturally by the sun, and any planet that has oxygen will eventually form ozone. And you will have this cycle going back and forth. In fact, Mars has an ozone layer, Venus has an ozone layer, and of course, Earth has an ozone layer. But this ozone molecule is a little bit fragile. It can't exist for a long time in the troposphere because it will react with water. And anytime there's water, it's going to react and end up going away. And it can't last up in the mesosphere because the radiation in the mesosphere is too strong. And it will blast it apart, and then it's not going to reform as well. Now let's go back.
So the stratosphere happens to have just the right conditions.
The stratosphere has exactly the right conditions. It's dry, and it's high enough that you're getting lots of that UV light, and there are enough air molecules that once you form ozone, it's going to run into other atoms. And so it'll run into other oxygen atoms. It will split apart and reform. The stratosphere is perfect place for this ozone layer to form.
So it's like the perfect sunscreen for us.
It is.
It lets all the good light through and stops the bad light.
It is. It's the perfect sunscreen for planet Earth. Now, to understand why we had an ozone hole, we need to talk a little bit about refrigerators.
Ooh.
So back in the day, back in the 1950s and 60s, refrigerators had a gas that would cycle through the fridge and cool it down. And so you have your fridge here, you have the gas here, and it's cycling through, and cooling your fridge. And a lot of the gases that were used were dangerous. You had sulfur dioxide, toxic, smelled terrible. You had methyl chloride, toxic and flammable. This means that if your fridge broke, if the back of your fridge broke and it started leaking gas, people could die.
Your whole house could start on fire.
Houses could burn down. This was a big deal. Ammonia was another gas that was used. This was toxic, flammable, and corrosive. So scientists really wanted to discover a gas that was safe. They wanted a gas that could be used in a refrigerator and that would not light on fire and that would not kill somebody if they accidentally breathed it in. And they invented chlorofluorocarbon.
Whoa, say that 5 times fast.
CFC, 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 CFC.
That's cheating. Wait. So chlorofluorocarbon, they just call CFCs.
Yes, because chlorofluorocarbon is a little bit of a long...
It's a mouthful.
Yeah, to say. And so CFC is the nickname for these compounds. There are lots of different types of chlorofluorocarbons, but the thing they have in common is that there is a carbon atom in the center that is holding on to a chlorine or a fluorine. So this one is one of the most common. It has 2 chlorine atoms and 2 fluorine atoms. But wait a second, Math Dad, I thought chlorine and fluorine were terribly reactive, right?
They're the halogens. That's right. They're in not the noble gas column, but the one right next to it. And those are the reactive ones. I remember that from chemistry.
So wouldn't this be a terrible molecule to breathe in?
Yeah, it'd be really bad.
Actually, no. It is remarkably stable. And it's because these molecules are bounded to the carbon so tightly. They're not going to go off and react with something else. They're really happy being stuck to that carbon. And so when you have chlorofluorocarbon, it's going to last for a long time. And when I say long time, I mean 40 or 50 years. So if
each little molecule is going to stay together for 40 or 50 years?
On average, if you take a balloon of chlorofluorocarbon and you pop it open and release that gas out into the environment, that gas is going to be stable and going to stay around for a long time. And that is not true of other gases like hydrogen or even water vapor. Other gases, they are going to react and change, and you're going to have different reactions happening. Chlorofluorocarbons, very stable. They used to do demonstrations with this where they would take tubs of the gas. Because this gas is a little bit heavier than air, you could actually fill up a tub with the gas, and then you could pour it down a staircase. And on the staircase, they would have lit a whole bunch of candles. And then as the gas went down the staircase, it looked like magic. The candles would just go out step by step. The problem with chlorofluorocarbons is that once it gets up into the stratosphere, where there is a lot more of that high energy UV light, then it breaks apart.
Oh.
And up in the stratosphere.
Oh, so it's because of the high energy from that UV light that we were talking about. The same thing that's breaking apart the ozone and the oxygen atoms.
Exactly. So the same UV light that can break apart ozone and oxygen atoms in the stratosphere can break apart the chlorofluorocarbon and release a chlorine atom. Now, chlorine, is a disinfectant. That's why we put chlorine in swimming pools. And it turns out that chlorine in the stratosphere is very different than chlorine in your swimming pool. The chlorine in your swimming pool is not going to make it up into the stratosphere. It's reactive. It's going to bond with water. It's soluble. But the chlorine that is released by CFCs in the stratosphere, it becomes an ozone killing machine.
Wait, is it breaking the cycle? Is that what I'm seeing?
Can you hear us now?
Hello. This should work.
Okay. Well, let us know if you can hear us now. Still can't hear you. No noise. Oh, no. Oh,
yes.
Yay.
Okay.
Thank you, Maurice.
All right. So
now it's okay.
Fancy microphone's gone, but we've got the regular mic.
And we have Science Puppy. That's what really matters, right? Okay. So we were talking about the ozone hole, and it looks like now we have lost, you guys. Sorry, technical difficulty. It looks like we've lost the ability to bounce back and forth between our different views, but we still have a couple images that we can share. So we will just adjust and keep going forward. So CFCs, they release chlorine in the stratosphere, and that chlorine then can cause the ozone to be depleted. And that's what has happened over the ozone hole. So if you have seen the famous pictures of that ozone hole over Antarctica, what's happening is that we're getting a buildup of chlorine gas over Antarctica because of the very, very cold temperatures and the formation of these clouds up in the stratosphere. And that is what causes the ozone hole. Now, it's not an actual hole, it's a thin spot. But that thin spot is a really big concern because it means that more than 50% of the ozone has been lost. What are you doing, Math Dad?
I'm switching the cameras. This should work because our audio stayed the same. We're good.
Okay.
All right.
Then can we pull up our slideshow?
Yeah.
Awesome. Someone give me a confirmation in the chat that you can still hear us. I want to make sure we didn't lose audio.
It was a brilliant fix. There's no chance I messed things up. All right.
All right. Thank you, Shyla. Glad to know you can still hear us. So let's take a look at what would have happened if we had not banned CFCs. And yep, what would have happened if we had not banned CFCs? And it turns out that we would have been in huge trouble.
Ooh.
Oh, Math Dad.
Oh, what have I got?
I
didn't go to the start of the slideshow. She's going to dock my pay, guys. All right.
So these are polar stratospheric clouds. These are clouds at high altitude. And anytime that you have temperatures that get cold enough in the stratosphere that these can form, then you'll have a supercharged ozone depletion. That means you're losing ozone. And if we had not agreed to ban CFCs, NASA did a study and they estimated that by the year 2064, we would have lost the ozone layer around the whole entire world. It would have been down to a low enough level that all of that dangerous radiation would have been getting through.
Whoa, just like go back. That you're saying by 2064, it would be super thin.
Yes.
That's kind of crazy. This is not the trajectory that we're currently on?
No, thankfully. This is not the trajectory that we're on. So the red line is what we expect to happen. The black line is the world that we avoided.
Okay. So up top is the green line. That's what we would have if there had never been the chlorofluorocarbons?
Correct.
And but we started losing
losing ozone. That's that blue dip down. And now we're recovering. And we expect the ozone to continue to recover. And by about the year 2075, we should be back to normal. But if we had not done that...
Ooh, that thing's going straight down.
It is. And take a look at the UV light. We would have had extremely high levels of UV radiation. This means that by the year 2050, so take whatever age you are now, add 29 years to it, and imagine how old you are 29 years from now. Mm-hmm. If we had not banned CFCs, then in the year 2050, going outside for just a couple minutes would give you a severe sunburn with blisters all over your entire body.
What?
All plants would die. All plants that were on the land would die. And we would only have life in the oceans because the first few layers of water in the ocean block UV light. Whoa. All right, let's go back to our main view now.
Okay, that is crazy.
Math Dad's trying to give you guys a hint about the where in the world mystery.
I can do this.
Good job, Math Dad. So
people saying how old they'll be. That's kind of crazy. So, I mean, it seemed like 2021 on that chart was already up in that danger zone where we would be suffering. Is that correct?
We would be. So we have less ozone worldwide now than we did in the 1970s because of CFCs and the damage they have done to the ozone layer. But fortunately for us, the ozone layer is recovering.
And so the reason it's recovering is because we stopped
producing CFCs. And it takes decades before they leave the atmosphere, but eventually they do break down and the atmosphere starts to recover and more ozone is produced. So the ozone layer is recovering, and the encouraging thing about this is that it just took an agreement. You had 100 countries that said, okay, I agree, we will not make CFCs, and it basically saved the planet.
Wow, that's pretty awesome. I'm super glad that they detected that this was going to be a problem, because sometimes you don't realize that there is a problem until things start getting bad. So the scientists were monitoring over Antarctica and realized that
Yeah, that there was
thinned?
a huge thinning over Antarctica that was happening every spring. And then it led to more atmospheric research. And now it's monitored really closely. You can actually look in real time to see what ozone concentrations are worldwide.
And so the consequence then of all that UVC getting through would be, just so we're clear?
So if all of the UVC radiation reached the surface of the Earth, pretty much every plant and animal would no longer be able to survive being out during daylight.
Ah!
You could only be out in the middle of the night. You could only be nocturnal.
Even plants? Because plants like sunlight.
Plants do like sunlight, but too much UVC sunlight is damaging. It breaks apart DNA and causes cells to be damaged.
So it's just too high energy.
Too high energy.
Well, that's crazy. So the ozone layer is like this magic shield. Like I remember, so there's this show called Stargate that I like, and the bad guy has this shield and it protects them from all these energy blasts. But you can punch the bad guy. The shield doesn't stop the weak things. But the ozone layers, it's kind of like that. It only stops the bad stuff and it lets all the other stuff through. It really is like a science fiction shield. It's that good.
But it's not fiction, it's real. The ozone layer really is remarkable.
Science fact.
All right, let's do our Where in the World mystery. Are you ready for this, Math Dad?
I'm ready.
And hopefully you didn't peek when we showed our pictures earlier. I'm going to give you just a half a clue. This is the only city located on 2 different continents. What city is this?
I think I know. Actually, I think I know this one. Is it Istanbul?
It is Istanbul.
Yes.
Good job, Math Dad.
Constantinople, but you can't go back to Constantinople. Been a long time gone. Yeah. So
Istanbul is our answer, and this city is incredible. In addition to being located on 2 different continents, it has one of the largest, oldest buildings in the world. This is Hagia Sophia, a very famous church that has been around for hundreds of years.
Oh wow, it's beautiful.
And was also built in a zone that's fairly prone to earthquakes, so doubly amazing.
I think that was like the first Where in the World one I've gotten right.
Good job, Math Dad.
It's about time.
Good job, Creative Koala, and everyone else that put Istanbul in there. Nicely done. And now we are ready for questions. And I want to just give a shout out and say thank you to everyone for hanging with us through the technical difficulties of losing our sound.
All right, so we'll do some birthday shout outs.
Yes. While Math Dad is pulling up the polls, I will do some birthday shout outs. So we have super happy birthday to... Gotta find my right date.
Today's the
22nd. I actually don't have any birthday shout-outs in my notes for today.
Nobody got any older? Man.
Well,
all right.
We'll do some.
No, I'm ready.
You are ready? All right, let's go.
All right. So for our first question, so go to itempool.com/sciencemom/live and tell me, what is ozone made of? Is it ozone atoms, oxygen atoms, nitrogen atoms, or chlorine atoms? Ooh. What is it made of?
Yuri asked a great question about refrigerants. If we stopped using CFCs, what are we using in refrigerators now? Mostly HCFCs. So it's a similar compound that has chlorine and fluorine and carbon, but it is built so that it will break down quicker and won't go up into the atmosphere.
All right, I'm going to finish and reveal the answer. The chat said oxygen atoms.
Correct. Yay for the chat.
Nicely done. So the chemical formula for ozone is?
O3.
O3.
3 oxygen atoms.
Nicely done, guys. Question number 2. Which layer of the atmosphere is the ozone layer in?
And great question from Aaron asking, how thick is the ozone layer? It is fairly thick when you're, well, maybe I better wait till I answer this one because I'll kind of give it away.
Yeah. No hints, Science Mom. Aaron trying to ask those questions to get a hint.
Go ahead and finish reveal. They know this one.
All right.
Stratosphere
Warmer than
is
the
correct.
air below, ozone layer had a hole. Airplane contrails white like snow in the stratosphere. So
it is several kilometers thick in the stratosphere, but it is most concentrated right at the bottom, right about 20 miles above the surface, or 35 kilometers. But when I say it's concentrated, I mean its most concentrated part, it's 15 parts per million. That's actually not that high.
That's not very concentrated at all.
No. There is less ozone layer in our atmosphere than there is carbon dioxide. And you'll remember from earlier, carbon dioxide is not a very common gas in our atmosphere either.
Not a really tiny portion. Whoa, so that explains why those CFCs could be so dangerous, because
we don't have a lot of ozone. And so if you have one molecule that's taking out 100,000 molecules, that's a big deal.
Indeed.
All right, next question.
Number 3, which of the chemicals below damage the ozone layer? We've got chlorofluorocarbons, hydrocarbons, carbon dioxide, freon. Ooh,
and Kara Rogers asked a really good question. Where can you find chlorofluorocarbons other than in a fridge? And they had a lot of different uses before we realized how damaging they were. So they were in aerosols. When you take whipped cream or like a spray can of spray paint, you need to have a gas in there that is compressed so that then the paint will spray out or the hairspray will spray out. So they were used in spray cans. They were used in fire extinguishers and the air conditioners and fridges and freezers. Those were the really big ones where they were used the most.
Good question. All right. They said chlorofluorocarbons and freon. Boy, did I almost stumped them. Like, look at that. D and B got the same number of votes. Does that one count as a victory?
Nope, you didn't stump them. Freon is the common or like the company name for one of the most popular types of chlorofluorocarbons. It's a chlorofluorocarbon as well.
All right, we'll call that one a draw.
No, they win, Dad.
All right. Number 4. What would happen if Earth had no ozone layer? So would the planet be the same? Would the planet be much cooler? Would all land-living plants and animals die? Or is it impossible to destroy the ozone layer?
And good question from Kunalin about black lights. What type of light does a black light or a UV flashlight have?
Ooh.
UVA is typically the light that they're going to have. So it's
the least dangerous
the
UV lights.
Yep.
All right. Oh man, one of the bars is getting all the votes here.
That means undefeatable science kids are retaining their undefeated streak, Math Dad.
Okay, they got lucky on this one. But yeah, all land-living plants and animals would die. That's horrifying. This is really strong radiation.
Yeah.
That this would do some serious damage.
Our atmosphere does a lot to protect us. And if you think that the UVC radiation is bad, be thankful for the mesosphere and the ionosphere, because there's even more powerful radiation up in space that the higher levels protect us from. Wow. So we definitely need an atmosphere.
So when you go to the doctor and you need to get x-rays, for example, they give you this protective coating and they just do it for like a
half a second.
Yeah, millisecond there. And is that also because that's so damaging?
Yes.
That's even more high energy, right?
That is. And if you're in outer space, you're basically getting hit by x-rays all the time. So
oh, wow.
Our atmosphere protects us from the x-rays and it protects us from UV radiation.
Oh, one of those answers said the ozone layer can't be destroyed. Is that true, actually?
We'll talk about that in a minute. Let's get through our other ones.
All right. Number 5. Which of the following could contain chlorofluorocarbons? Hot air balloons, refrigerators, air conditioners, spray cans, fire extinguishers. Select all that apply.
And then back to that question, could the ozone layer be destroyed? Well, it can get down to a level that's so low that then it's not blocking that radiation. And for us, that would be like it's being destroyed. But anytime that you have oxygen in your atmosphere and that you have UV radiation, you're going to be forming new ozone. So you couldn't get it down to where there wasn't a single molecule of ozone. But if we got it down to levels that are the same as below the stratosphere, that would be catastrophic.
This one has an interesting curve to the choice of answers.
All right, finish and reveal.
So they said for sure refrigerators.
Yes.
But they also mentioned spray cans, fire extinguishers, and air conditioners.
Those could all contain chlorofluorocarbons. Hopefully, newer ones hopefully do not. But an old fridge or an old freezer, it could. So you don't want to just throw an old fridge into a landfill. You want to make sure that you dispose of it in the right way so that that gas doesn't leak out into the atmosphere. A hot air balloon, no chlorofluorocarbons, just hot air, regular hot air.
All right. Number 6. There is more ozone in the ozone layer today than in the year 1970. True or false?
Are you hoping to stump them on this one, Math Dad?
It's inevitable, Science Mom.
I don't think so.
Yeah, that's okay. They'll try their best. And I won't make fun of them too much for when they don't succeed.
You're going down, Math Dad.
Ooh. I don't think they're getting it. I don't think they're
All
getting
right,
it.
let's finish and reveal.
All right. Pulling the plug. They said false.
And they're correct. We are about 5% lower worldwide with the ozone concentration in the stratosphere now than we were in the 1970s. But the good news is within the next 50 years, we should recover and get back to that same level. Next question.
All right. Our final question of the day. True or false, Venus has an ozone layer? Okay. This is the one where I stumped them, Science Mom.
I don't think so, Math Dad. Oh, look at how sleepy Kaladin is.
Oh. You have a good life, don't you, doggy?
He had a good walk this morning. And then we always take him for a nice long walk / run in the morning. And then he comes home and takes a good nap in the morning. That is his routine.
Okay. Finish up this poll. They said true, Venus has an ozone layer. Man.
True. Good job, you guys.
Man, this one I'm sure was going to stump them. Like, you did mention it, but it was so fast. And that's ridiculous. Why would Venus have an ozone layer? Okay, it has an ozone.
Real fast before we do our victory dance, there was a great question from Kara. Does anything with an atmosphere have an ozone layer? Most planets with an atmosphere have an ozone layer, but not all of them. So Jupiter, most of Jupiter's atmosphere is hydrogen and helium. That's not going to form ozone. You have to have oxygen. But Mars, Earth, and Venus all have an ozone layer. And then certain of the moons around, like Ganymede, the moons around Jupiter, they have ozone layers too.
Wow,
cool, right?
I didn't even know they had an atmosphere.
A couple of them do, very, very small atmospheres. And now, shout out to all of the people who were requesting the orange justice, because Math Dad filmed in front of our colorful lights. He filmed a victory dance just for you of him attempting to do orange justice. Here we go. There you go. That is his attempt. It was, what did you?
My defeat dance was pre-filmed.
It was, it was not easy, not easy. I'm going to answer a couple more questions and then we will wrap up. So great question from Elliot. If you could wear ozone, would it be a good sunscreen? I love this question.
Wow.
It's very, very inventive and creative. The answer is no. Ozone would not be a good sunscreen because although it would block UVC light, it would do it by splitting apart into oxygen and then a free oxygen atom. And remember, free oxygen atoms, these are dangerous. They damage our DNA and they cause a lot of problems with our cells and our membranes. And so the more ozone you had on you, the more this would be happening and the more damage would be happening to your skin.
No, but I like the attempt, though.
Good question, yeah.
That's clever.
And then Remington Wolf asks, what is the most powerful type of light? If you look up different types of light, UV light is the most powerful one that we usually talk about. But beyond that, you have X-rays and gamma rays. Gamma rays are typically the most powerful. And, ooh, Ibrahim is saying we were going to tell us a crazy story. Didn't tell us yet. Is the story coming up? The crazy story, really, the story that we're telling is just how close our planet got to losing its ozone layer.
And it was self-inflicted too, because these chlorofluorocarbons weren't naturally occurring, right? So we
Correct.
invented this solution to this terrible problem of not being able to, for our refrigerators, we had these awful chemicals, and we're like, aha, we came up with this wonderful one.
A better chemical, but then it turned out that better chemical was really dangerous to the ozone layer, and we had no idea. So at the beginning, when I mentioned the crazy story, that was that whole big story about ozone. That's what I was referring to.
Oh.
Good question.
Yeah, so we almost destroyed the planet, but then we're rescuing the planet.
And then Aeneas asks, what would happen if a tardigrade inhaled ozone? And I have to say, if I were going to take a guess about, is there another type of animal that could actually survive ozone exposure? A tardigrade might be the only one where I would think, maybe, just because they are so tough. But no matter what you are, whether you are bacteria or an animal or a plant, ozone will cause these little free oxygen atoms, and those will damage your cells. And so you don't want to have a free oxygen atom going around in your cells.
Great questions.
Yes. Good job, guys. All right. Thank you so much for joining us today. Apologies about our technical difficulties with losing sound, and thank you for your patience while we troubleshooted that. And we will see you guys on Wednesday.
Work hard, grow smart. We'll see you next time.